Thanks, Bob. It's hard to follow that kind of introduction and Amal's excellent lecture. But I'll say one thing, it's easy to lead when you're following great students. And I've had a lot of really great students. Bob was the TA for the class that built New Pearl. We talked about constructive math, and we sketched out this idea without giving it a name or anything. And the entire class, it was like 17 students, wanted to work on the project. This didn't go over well with my colleagues, but we got New Pearl built, and it then occupied my life ever since. So anyway, this talk is not about New Pearl, though. The title, I have written a lot of pages in LaTeX, and we'll probably put them on, post them here. And the title is 2 Lectures on Constructive Type Theory, and that's a very simple title, and this is Lecture 1. So that's the title of it. But my charge here from Zaina and Bob was to not only talk about technical matters, but to talk a bit about the philosophy and the history, where it started and where I think it's going. And I'd like it if in the second lecture tomorrow, if you all are still here on Saturday, that we spend maybe the last 20 minutes in a discussion. You know, Mark and I will be up here and we'll take questions. I've lectured for many years at the Mark Doberdorf Summer School, and that always happens at the end of every day. The lecturers face the music, right? They get questions from everyone. And these are some of the most lively moments, as I recall, over the years at Mark Doberdorf. So I hope we can do that. And I posed myself 3 questions for us. I'll state them right now. So I want to know, what are the most important and fundamental ideas in computer science and mathematics that can be best expressed in constructive type theory? You know, where does this type theory have a lot of purchase, a lot of influence on both computer science and mathematics? So that's one side. And then the other side is where are we weak? You know, where do we have trouble competing with set theory? Because if you talk to mathematicians, set theory is their default language. And there are some wonderful quotes they love to say. Look, every theorem in mathematics can be explained in ZFC set theory. It is just a result in that set theory. And that's adopted essentially worldwide by almost all mathematicians except the constructivists, and that's a pretty small group, mostly in Holland, right? And a few of them scattered around the world. Why aren't, could that ever happen, that people will say a few years from now, decades or so from now, you know, we can express everything in computer science very precisely in constructive type theory, and the mathematicians agree, and they say, yeah, we do that too. Could that happen? So I want to talk about that. And I'm also very interested in how proof assistance can have a large impact on research and education. And I have this belief from talking to a lot of undergrads who get very excited about proof assistance, principally Coq. That's the one we use most for teaching at Cornell. And the students just get incredibly excited about this. They also get somewhat misled. I mean, I'm going to prove a theorem to you tomorrow called the Bloom size theorem, and I kept asking the students to tell me, like, what's the fundamental idea here? And I narrowed my question down on some of these things to, okay, why is this idea true? What's the fundamental reason? And very eager students waving his hand. I said, okay, yeah, what is it? Because Coq said it was obvious. I said, wait a minute. That's your explanation for why this is true? I said, I never want to hear that again in class. Not because it's Coq, but I want your idea. You know, what were you thinking? Why is it true for you? So that's part of the second question. The third one is what ideas will you miss out on if you only know one of Agda, Koch, Newpearl, HOL? What are you going to miss if you know one of them and not the others? So that's, those are questions I'd like to get to. But the outline, okay, I actually have a very precise outline of what I'm going to talk about. So let's put it here. So the first topic I want to talk about are what I call the core logical types. And this is the part that we all agree on, right? So Newpearl, Agda, Koch, we all understand these core types and how through propositions as types they give us logic. So I want to talk about that, why they're so important and so forth. And I'll talk a bit, as Zaina requested, about the history of this. I'll be briefer than I had intended to be, so we don't spend too much time on that. But the history is fascinating to me, so we'll talk a bit about it. And then I want to go beyond the core types. So you've got these core logical types, but indeed, and this is, the core ones are the center of this idea of propositions as types, right? Also called, it goes by many names, Curry-Howard isomorphism. That's my least favorite name because it's not really an isomorphism, but that's okay. And it has several other names, and probably there are 20-some people. The book called The Curry-Howard Isomorphism traces the history and credits about 20 people with coming up with this idea. But it's all about these types, the core logical types. That's what this is about. But I want to go beyond these and show you something that I think is really the dynamic of this whole field. And that is that it's, this thing is a two-way street. So you can either start on the logic side and think up the types, or you can start with the types and you'll find some of them are logical types. So we want to go both ways, at least examine the two directions on that street. And one of those directions I'll talk about today leads to a new concept in logic, so I'm going to call it by its logical name. And I think part of what I'm going to do in my time is stress a lot the connections to mathematics, because Amal did such an amazing job, and Bob as well, talking about the applications in computer science. But I'm interested in the applications to logic and mathematics as well. And one of the things that happens when you see that this is a two-way street, you bring into logic some new operators. And in particular, the operator that Mark has talked about is this new quantifier, which is a uniform for all. And we'll talk about it in more detail. But this leads to a fundamental new idea in logic called uniform validity. And I'll talk about that because Mark and I published in last year, 2014, a solution to a long-standing open problem. It was open for about 64 years to give a constructive completeness proof for intuitionistic first-order logic. People didn't know how to do that. They tried based on its standard semantics. There was only a completeness proof with respect to Kripke models. And we managed, because we had this new type, we noticed something and were able to push through over a couple of years a solution to this problem. And our referees, we had a lot of referees on this paper, and many of them said, this is no fair to call it a solution to a 64-year-old open problem because you guys introduced a new idea, a uniform validity. but it's an if and only if idea, right? Things are provable if and only if they're uniformly true, and we found the other direction. But the other referees said, wow, that's a cool new idea in logic, and we should publish the paper. So it's out there, and Mark is actually implementing this thing in New Pearl, which will give some pretty neat ways to take a realizer. Just you write down a program, and you say, this is the program that realizes the proposition, and Mark's algorithm will give you a proof in first order logic. So that's pretty cool, but we wouldn't have gotten to that without the two-way street idea here, that you can take types and think of them as new logical operators. Okay, and then I'm going to talk about an idea that I like a lot. Mark keeps finding things that I shouldn't like about this idea, but I'm going to try to convince you it's good. I'm just going to call it right now insights. So that's actually there is a result, but insights into, say, classical logic. Okay, so that's a safe way of telling you that I think we have a new and really good semantics in constructive type theory for classical logic. And in fact, classical type theory. We can turn this type theory into a classical one. I think it's pretty cool, but you'll hear what Mark thinks about it. But anyway, you'll get to make up your own minds on that. I'll probably get to that today. And then we'll just look ahead like Amal was doing here and see what's coming down the road, the way she was doing on open problems, really interesting open problems to attack. All right, so that's the idea of this lecture 1. Lecture 2 is going to start with a proof of one of my favorite theorems about the difference between Coq and New Pearl. See, the Coq programming language is what I call a sub-recursive language, right? All of its programs are total. And New Pearl is a universal programming language. It allows partial recursive functions using Kleeni's name for this. And there's a striking result about this from many years ago when that was my passion. When I was an assistant professor, I loved sub-recursive languages. I thought this was a really cool topic, and I had enough results there to get promoted, so I liked the area. But they're very different, right? These sub-recursive languages have a lot of nice properties that Coq enjoys. And this was the kind of language that Gödel loved. He wanted the Herbrand Gödel computable functions are the total computable functions, right? All the total computable functions, Turing total functions. And that's what people focus on. But and here's an exercise. First 10 minutes, we have an exercise. Why isn't there a programming language for those? You should all know the answer to this. There is no programming language. There cannot be a programming language for Gödel's favorite class of programs, the Herbrand Gödel computable functions. So why is that? There's a simple exercise, not too hard. So what Coq has is a subset of those, right? And reasonably small subset. And it's more like the primitive recursive functions. But there is an amazing theorem that you'll hear about tomorrow, that it's called the Bloom size theorem. And it says these subrecursive programs sometimes are arbitrarily longer than the corresponding general recursive program, or a partial recursive function. And that's sort of surprising, but the reason I want to bring that up in the second lecture is that students who use calc complain to me often saying, wow, the program I got was just humongous. Why is it so big? Why is all this stuff there? So if you've had that response, this theorem will show you why and why it's going to happen. Okay, so let's get on then to the first thing, the core logical types.
Question?
Yeah.
In calc, it's straightforward to write an interpreter for a Turing-complete language where one of the inputs to the interpreter is a proof of termination.
Yeah.
How does that not get around this problem?
Well, that gives you, for all the ones for which you can prove termination, you've got it. But
this tells us some termination proofs are very large.
right. Yep. That's exactly what it is. Some termination proofs are very large. But yeah, you can, and it's true, you can do that, but you're not going to get the Herbrand-Gödel computable functions, right? Nobody's going to get those. You have you could argue that you have just as good a chance of getting close in any language, but in, yeah, okay, but you're going to pay the cost when you prove termination. Okay, so let's look at the core logical types. What are they? So if you're writing down from a logician's point of view, you would say, well, I have and, or, not, using false, implies, for all, and exists, right? You need all those guys, but you can boil this down to saying, well, if I use the for all quantifier, that's going to also pick up implication, right? And if I use the existential, I'm going to get and. So you really need just these two guys and or. That's going to give you, and you'll need some way of expressing not, and we have the void type or false there. So those are the standard logical types. And I'm assuming we all know these cold now, right? You've seen this during the, yep.
Could you explain why exists corresponds to and?
Oh, the exists here? Yeah, so let's look at what an existential is here. Let's say I write, there exists an element in the domain D such that P of X holds. The realizer for that is a pair, right, where you're going to get D, and then you're going to get a proof here of P of that proposition. So the elements there are ordered pairs, and that's what you need to realize an and, where you wouldn't have dependency. This is a dependent product, if you like, a dependent Cartesian product, and is an independent Cartesian product. Right, so for A and B, if I write down A and B, that turns into the product type, A cross B. The realizers are pairs, the realizer for A and the realizer for B. Are we all good with this? Right? I mean, okay, so those are the core logical types, and I think, we know a lot about them. So they've been studied for a long time, and I'm going to tell you the history. The propositions as types idea is centered on this. And I'll talk in a few minutes about the history of it. But I think I should explain a couple of proof rules here, just so you can see on the board the style that Mark has been illustrating, this top-down style. So let's just pick something we want to prove, and I'll state the way the rules look. So we have a sequent calculus with hypotheses here. So this could be just a list of your hypotheses. And suppose you want to prove A and B. We just did that example there. The way we do it in this top-down thing is we say, okay, I'm going to give the rule, by what rule to prove, or the tactic name, and then we're going to generate sub-goals. Okay, so our rule here for this is pair, in a sense. So we write the thing like that, because we know we're going to go after a pair, And this generates the sub-goals to prove A and B. And when you do that, let's suppose you finish the proof here, you got by something A there, and you got by something B by doing a sub-proof here. You did a lot of work. We then think of just substituting the realizers for the sub-goals into this pair construct, and that gives us the realizer for the AND, right? So that we like this top-down style. It's an LCF style, but this was, and the R in Perl, so new Perl is version new of the PRL system, and the R in there stands for refinement logic. So it's program refinement logic. And Joe Bates was very keen on this idea from Nicholas Wirth that we prove by refinement. He was an AI guy. And Tim Teitelbaum at the time was doing the synthesizer generator, which supported this thing wonderfully. So all of our rules are read that way. And again, every time we submit a paper to the logicians, they have a fit. They say, why do you guys do things upside down? Your proof should all be hypotheses first and go sub-goals. Well, we just say, could you learn to live with that? And if we've got a good enough result, they will. But sometimes they just get so mad. You know, it's like at computer science, they say, you computer scientists do things your own way. You know, why can't you follow our style? We say, well, you can't implement it as well. This is what you're doing. You're taking a goal and you're trying to prove it. So the AI people love it. So when we talk to the AI guys, they say, wow, finally the logicians are thinking the way we do. So let's see how we do implication. So what do we do there? We just write out the lambda, and we're a little biased by the synthesizer generator using McCarthy's abstract syntax, so we write it like that. And it says, okay, you're going to build a function, and this variable x is going to be the input to the function. And that generates a sub-goal here. We say, all right, I've got x of type A, and now I'm trying to prove B. And you're going to do some work building a subtree, and out will come this B that is the proof of B, and you just stick it in here, and this B will perhaps depend on the x. So the realizer is going to look like lambda x B with the x in there. All right, so that also shows you, when you write this thing down, you're introducing this variable here because you're doing a lambda, and the variable tells you how to name the hypothesis. So it's sort of nice. You get to pick the names for your hypotheses. One thing about new Perl that we won't talk too much about here is that before you can prove anything, you actually have to do you have to know that it makes sense, right? So you have to prove that this guy right here, this proposition that we're trying to prove, you have to show that it's in some universe I. And the universes come from Russell's type theory in a way. So you can think of this universe I, it says type I or proposition I, whatever. But we use the term universe following Martin Loff, who noted a really cool thing, that this is where the greatest mathematician of the 20th century, Grothendieck, injected some idea into type theory. Grothendieck said, you know, you guys are fiddling around here with these universes. You should just use something that's closed under all your operations, and he sketched out how it should be done. He did it for set theory as well, and they call that set theory Tarski-Grothendieck set theory, and it's the only one that's implemented and it was still widely used by the Mizar system. So anyway, before you can prove anything, you have to know that what you're proving is sensible, and that is an idea that goes back to Frege. And he introduced this symbol here, this turnstile. In fact, when Frege did it, he would write this thing with one line instead of the turnstile. He said that you first have to know what you're proving, whether it makes sense. So he went into that. He used the word sense. Does what you're trying to prove make sense? And if undergrads would get that idea, it would save us a lot of trouble, right? And that's one thing that Koch helps us with. They can't start proving total nonsense. So they get the proposition checked first. Now, we do that checking in New Pearl simultaneously with the proof. So we're building a proof that everything makes sense as we try to prove it, which was, I think, a pretty cool design idea, which we debated for a month or so in seminars. Okay, so this is what the rules look like. And here's an interesting observation that motivated this completeness result I'm talking about. When you get to the OR rule and you want to talk about classical logic, so now you're trying to prove an OR here, A or B, and constructively, you have to do this nasty thing of proving which you have to say, all right, I'm going to do the in-left part, and I'm going to prove A. And mathematicians like to be able to say, you know, I don't want to commit here, especially when I'm trying to prove A or not A. I don't want to commit either way like that. I just want to say that's true. So when I was teaching this style here, this top-down style to undergrads, you can't start out with constructive logic because they actually read other books and things and they'll tell you, what are you talking about? Everybody else. So here you need a name for this. So I called it magic because and I didn't tell them why, but I said, okay, magic. And that rule, magic, is the only one where the realizer needs the proposition, right? You have to stick the proposition name in there because what does magic have to do? It's got to look at that proposition and tell whether it's true or not. And if you don't give it the proposition, it doesn't have a chance. But that is the only rule when you're doing classical logic. If you look at all the other realizers, nowhere do they mention the proposition if you use an untyped language, as New Pearl does. We start with a totally untyped programming language, so there's no types on these things. And one thing you notice because of that is if you take this guy away, take that rule out, every other proof rule is giving you a uniform realizer, something that doesn't depend on the type. And that's what led Mark and me to think up this idea of uniform validity, which we could define using the intersection type, which I'll show you about later. But that's something you should notice. If you just write down the rules, or you look in any of in the New Pearl presentations, you'll see that they don't mention the proposition. And I'm going to show you how we can get away without using it here for classical logic later in the lecture. Okay, so that's propositions as types. So where did it come from? You could ask. So you could say, well, it was Curry-Howard, but I prefer to take this history way back. But let's just stop for a moment with Brouwer. Well, actually, maybe that's unfair because, we're very, we didn't come believing in Brouwer. We got dragged into understanding that Brouwer was right by many, many experiences. I did not want to ever mention Brouwer's name among my colleagues because they all thought he was nuts. The opinion about him generally as well, he was a wacko guy who had this crazy logic and nobody believed him and only the Dutch and that's it. So you don't want to talk about Brouwer too much in the beginning if you want students to work with you. And so as a matter of fact, the thing that allowed us to build New Pearl was when we read Bishop's book on analysis, because in there, he said, look, I want to do analysis constructively. I want to do real analysis constructively, but I don't want to get into fights with people about it. I want everyone to be able to read this book, whether you're a classical mathematician or not. And then I was so taken by that idea that we invited Bishop to come and talk to the department. I wanted everyone to hear this, and I didn't realize how famous he was as a mathematician. So we invite him to talk about constructive math, and the math department hears about it, and they say, oh my gosh, he's got to come over and talk about his stuff. So he just gave a lecture in the math department after he lectured with us on beautiful, complex analysis. And he never said the word constructive at all. He just gave this result, this new result that he had in complex analysis, and the mathematicians were beaming. And he didn't say anything about constructivity, but the whole proof was constructive. He just said, look, this is a beautiful result. And so inspired by that, I taught the whole course, the required course on computing theory that I think is one Bob was talking about. I taught it all constructively. Everything I did was constructive. But I didn't say that. I just gave constructive proofs wherever I could following Bishop. And we were able to do the whole course. And then I told him afterwards, by the way, everything here can be implemented in a programming language. And they said, oh my gosh, really? I said, yeah, we could do that. But don't mention that guy's name. And don't say constructive mathematics, say computational interpretation of mathematics. So then they were convinced that they should work with us and build this thing. And Bob was the TA in that course, and he had to be part of this conspiracy of don't mention Brouwer. Okay, but once we got into this, we realized, I remember Mark coming in one weekend after he had spent the whole weekend proving some result of Dexter Cozen's and Alexandra Silva's, and they kept using continuity every place, and he said, you know, I had to prove all those blasted functions were continuous to keep them happy, but we know by Brouwer that they're all continuous, so I wasted a whole weekend just because we don't want to talk about Brouwer. So couldn't we start thinking about this? Now he and Vincent have proved Brouwer's continuity principle is true in this world where you've got certain kinds of exceptions. Anyway, Brouwer wasn't the first guy who was a constructivist, right? It goes all the way back to Euclid, right? So Euclid, geometry, was a geometry of constructions, right? If you said you were going to bisect an angle, you bisected the angle. And if you tried to trisect an angle, you couldn't do it. And people didn't know why until Gauss. But this was a language of constructions. And if you don't believe that, just look at his proposition 2. Proposition 2 is the proposition that says, if you've got a line anywhere, and you've got a point, you can copy that line to the point. And you think, well, that's trivial. You just take your little marker, you take your compass, you measure it, put it down on that point. But the compass that poor Euclid had to use was the collapsing compass. The compass was only to draw circles, right? You could put the thing down, draw a circle, and that's it. And when you picked it up, it collapsed. So he couldn't do the very first construction he wanted to do required a clever, really, really clever theorem that says you can simulate a non-collapsing compass with a collapsing compass. That's his proposition 2. Constructive right from the beginning, and allowed him to then do a lot of other very nice constructions. But the Greeks, they didn't believe. So it's not just Euclid, except we have to put Aristotle up here, because Aristotle did logic, right? And logicians have always been on the outside of math. And so he was the philosopher worrying about the scientific method and all that. And Euclid really wasn't using anything more than his axiomatic method. You could count that in there. But But Euclid really was doing everything almost completely constructively. Okay, but as I say, nobody touched the logic for hundreds of years because Euclid started a whole long tradition. Most of mathematics, if you look at the Gauss's thing, what did Gauss love most? Of all this beautiful math he did, he constructed a 17-gon, which nobody had been able to construct until then. And that he put on his tombstone. How you built, he showed you could build a 17-gon. Okay, so there's Gauss, one of the greatest mathematicians in history, constructing stuff. That's how he knew things existed. And he invented induction, right? In the constructive way that we like to think of it. Okay, and it goes on and on. You've probably heard of Kronecker, right? His famous speech. People portray that after Brouwer, people looked back at Kronecker and had a dimmer view of him, thinking he was like maybe encouraged Brouwer or something. But Kronecker, what did he say? He just said something like, the good Lord gave us the natural numbers, and all else is the work of people. He said men, or is mention work, people work. Okay, well that's pretty good. I mean, because I think the far future, if you read Darwin Among the Machines are going to start talking to us when they're grateful about their ability to do math better than we are. And one of those machines will give a speech. And it'll be like Kronecker. He'll say, you know, those humans, they gave us the numbers. They gave us the numbers. And they said to us, go machines and do math. And we did. We went forth and we did math. So it'll come back. You know, the way Kronecker did, he was trying to be encouraging. And like, you humans, we humans, we will do this work. Okay, but he got, so math started to get a little different after Hilbert. You know, he solved this problem that had constructive content, but he did it non-constructively, and people were saying, oh, what is this method of Hilbert? So Hilbert started a little bit of a battle here, and I guess he was a feisty kind of guy, Hilbert, because he was picking on Kronecker, and Hilbert was regarded, after he solved the Gordon problem, whatever it was, he was considered the greatest mathematician in the world. And Brouwer was just coming up in the world. He was a young whippersnapper who wrote in 1907 his PhD thesis where he questioned Aristotle. He's the first guy, you know, so we're going back 2,000 years. He says, you know, maybe Aristotle got it wrong with P or not P. But he didn't make a big deal of it, of this, because I think his advisor said to him, his name was Egbertus, L-E-J, Lucian. But I said, Lucian, lay off of that constructive stuff until you're really, really good. Then you can start talking about it again. So he took a vacation on that stuff, and what did he do? He created topology. Not bad. So, yeah. Okay, so now he becomes very famous, and he's starting to compete with Hilbert as one of the great mathematicians in the world. And Hilbert says to him, come to Göttingen, the center of the world. Oh, so Brouwer goes and visits. He says, well, you guys don't speak Dutch here. What's going on? And he had other reasons. So he turned down Hilbert. He didn't accept the offer. And then he realized, wow, Hilbert just anointed me. So there's Hilbert, and then it was going to be me. So now I can follow my thesis advisor's advice and start telling people how wrong they are. So he starts telling Hilbert how wrong he is. Not a good idea. On top of everything else, so this started the thing called the Frog and Mouse War that is in the history books there. And so he turns Hilbert down. He then starts to say, you know, Hilbert stole one of my ideas. Apparently, when they were buddy-buddy and Hilbert's trying to get Brouwer to come on board, Hilbert was thinking about meta-mathematics. How do you prove that theories like geometry are consistent? And he had this idea of formalizing, right? So he said, we're going to formalize geometry, and instead of talking about points and lines, you can talk about tables and beer mugs. It's just going to be a game. So he turned math into a game, like chess. And Brouwer claims in one of his memoirs that he and Hilbert are out walking in the mountains, having a good time discussing this, and he says, yeah, I have the same notion. I call that secondary math. There's primary math, and then there's the math you do about the math. So he was expecting that Hilbert, and he would agree here, but he claimed in written material that Hilbert stole his idea and took off with meta-mathematics and stole it. So he starts telling everybody Hilbert is a thief on top of everything else. So Hilbert started the Frog and Mouse War. He was the head of the most important, the Math Annalen Journal, and he fired Brouwer. He said, you're off the journal. Brouwer reads the regulations and says, you can't fire me. All you can do is fire everybody. So Hilbert says, okay, I'm firing everybody, including Albert Einstein, who was on that journal. So he fires them all, and then he tries to hire them back. He says to Albert, okay, you come on back on. Albert Einstein says, I don't want anything to do with you guys. You're nuts. so go ahead, build a new journal there. But anyway, Hilbert went about destroying Brouwer's career for quite a while. Brouwer disappeared and helped his sister run a drugstore for a long time. And that thing is called the Frog and Mouse War. So what happened, though, is Brouwer had some excellent students. I tell everybody your history, your legacy is going to be your excellent students, people like Bob. So Hilbert had some very excellent students, and Brouwer also had this student Heiting. And Heiting started to write up Brouwer's ideas in just logic and made it much less philosophical. Brouwer's idea of a proof, by the way, and this is something we should understand, for Brouwer, and we're not there yet, a proof is a mental construction, right? It's not something that you write down like this. You don't have to write proofs down. These are things you do in your head to convince yourself that something is realizable, constructible. But Heiting said, look, let's just compromise a little bit and write down the rules. So he wrote down the rules of Brouwer's logic, and did it for arithmetic, and we call that arithmetic to this very day Heiting arithmetic, so HA. And this inspired Kleene, who was one of Alonzo Church's most productive students. And Church was very interested in what Brouwer was doing. So Kleene went off to learn intuitionism from Heiting in Amsterdam. And he came back with an idea of realizability, that you could actually interpret, and that's basically propositions as types. So Kleene did this about 1938 or maybe 40, say. We don't know exactly when his manuscript was published, was written. But then World War II started, and he served in the Navy as an officer, and he wasn't able to do any writing for a long time. So he didn't publish this thing until 1945, but he published a realizability semantics where he essentially gave the interpretation that we give now, but he used indices of recursive functions. So instead of putting this here, he would put a Gödel number of a function like this. So the thing would be realized by a number E. And you might wonder, why didn't he use the lambda calculus? Why didn't he do the Curry-Howard thing? Because he invented, along with Church, the lambda calculus. So I wrote him a letter. I was a student of his, so I could ask him, okay, why, when you did all this, why didn't you use the lambda calculus? And basically his answer was, I had to translate everything we did in the lambda calculus into Gödel numbers and all that stuff because people hated that. They just didn't understand the lambda calculus. And so the realizability was a response, and in particular, Gödel hated the lambda calculus. So he just didn't like it. He liked either his Herbrand-Gödel recursive functions or Turing machines. He said, the Turing machine, that's it. And he called that the only absolute concept in all of mathematics. And Gödel at that time, was the very eminent and famous mathematician. When he says things like this, you pay attention. So, Kleene started saying, well, okay, I should do it Gödel's way. And indeed, we know Gödel was a pretty good programmer, by the way, in his primitive recursive arithmetic. He would have loved Coq. That was his language. Because we know when he bought the first copy of Principia Mathematica, he kept all his receipts. So you can see he bought Principia Mathematica on a certain day, and he basically programmed it in primitive recursive arithmetic. How do you define the formalism? How do you set up everything? So he arithmetized Principia in order to get his theorem on incompleteness. And we know he did it pretty fast. It took him less than a year to code like crazy. If you look at his paper, it's full of programs, primitive recursive programs, to do the syntax, to build up proofs, the whole bit. So he was a pretty good programmer, but not in the lambda calculus. And by the way, in the theory A community, the theory world is divided into two bits. Theory A, algorithms, real theory, hard complexity results. And theory B, that's what you guys are right now. Theory B, semantics and all that stuff. So the theory A guys still wonder what the lambda calculus is. They say, come on, the right model is Turing machines, and they cite Gödel and all that, or random access stored program computers. But anyway, Kleene had to avoid all that, so he used realizability, but he had the whole idea of propositions as types. He just had to state it in this strange language. Wow. Telling too many stories. When did I start, Bob? Like right on time? 10 past? Oh. All right. Well, okay. So there's too much history. Okay. So let's see then what happens when you go beyond these types. So let's look at what happens beyond the core. So where are we? We've done history. Now we're going to do beyond the core type. So let's think about some other types that are pretty useful. And you've already seen the intersection type. That's been used in these lectures. But let's pick the simpler one and see if it makes sense to you in a logical way. So if we have, in NUPRO, if we have two types, A and B, we can talk about A as a subtype of B. All the elements of A are elements of B. And this is made easy to understand because, as I mentioned in the proof rules, all of the NUPRO terms come without decorated types. They don't have types on them, right? So what would be the logical meaning of this? if we tried to think of that as a logical operator. Every object in A, every element of A, is an element of B. That's what it means. Okay, so if you have A in A, then A is in B. Okay, what kind of logic is that? What might you call that operator? Is anybody? Right, okay. Bob, say, whoa, lost the whole marker there. Well, we really lost the whole marker. Okay, okay, so let's write it bigger. Okay, A subtype of B. What kind of logical operation is that? Does anybody have an idea? Yeah. Yeah, it's what kind of implication would you call it? It is an implication, no doubt. If you're just dreaming up a name. So you got it, but you don't want to just say it's implication because it's a special kind, right? Yeah, trivial, but that's a word you want to avoid if it's going to be your idea. If it's my idea, you could call it trivial implication. But it wasn't my idea. This was, I don't know, Knack, somebody in the group, but didn't make it. So we called this immediate implication. Pardon? Yeah. So it's immediate. You say, look, okay, if I know A, any justification for A is going to be justification for B. So that's not a bad operator, right? You wouldn't mind having that in your logic if you could find a use for it. Okay, so, and we did. I think one of the papers that Jason Hickey wrote was about that. But let's take this intersection type now that we've heard a bit about. So what are the elements in this type? So there are things, these untyped terms, that are in both A and B, right? So this is certainly a kind of and, right? It's a new and, a uniform kind of and, where you're saying, and indeed this idea goes all the way back to Pottinger in 1980. From Capo and Dazzani, right? They were doing these types for programming languages. They had this, and Pottinger, well, I forgot, I wasn't planning to do much history here, but this operator caused the type checking algorithms to be a lot more complicated, but it's been around for a while. And then we talked already a bit about this quantifier now, this uniform. So here's the uniform for all that Mark frequently writes. What do you do, Mark? Is it like this, right? So that's the quantifier that says, look, I'm going to be able, independent of what the A is, to give you a realizer here in B. So you can view this then as this uniform for all. And as I mentioned before, when we looked at the proof rules of the propositional and first order logic, we realized that every realizer was uniform in there except for the classical thing. So these turn out to be very interesting, and that's part of this two-way street. And I believe we'll discover more types that have interesting logical meaning if we're just aware of this two-way nature of that correspondence, propositions as types. Okay, now one of the other types that doesn't get such heavy use, but I thought this type would be one of the favorites of the world after we introduced it, the quotient type. So following Bishop's definition of a type, he actually defined a set. So when Bishop, in his wonderful book on analysis, talked about a set, he said, to define a set, you have to do two things. One, you say how to build its elements. how to construct, say, its elements. And then, before it becomes a mathematical object, you have to define equality on those objects. Define equality. And he had this very nice insight, I think, that what makes mathematics abstract, what makes it something other than programming, is equality. It's there. And in programming languages, we teach people not to use it, right? In Fortran, I spent a lot of time teaching Fortran. And one thing you realize is you don't want students to use the Fortran equality on anything. So you say, avoid that, because it's not particularly well behaved. But for real mathematical programming languages, you want to define equality. And we said you should be able to change the equality on a type by quotienting it. So for example, if you want to do the integers, say z mod 5 or something like that, what you're talking about is you're going to change the equality on z. It's got its standard equality, and now you want to say the equality is just going to be mod 5. And that seemed to me to be a really elegant way to do this compared to set theory, where what do you do in set theory for z mod 5? What are the elements there? Equivalence classes, big things you're not going to compute with, right? So this seemed to me really nice. And Dana Scott was in the audience when I was lecturing about this back in 1983, and he said, wow, these ideas are really cool. That you should definitely put this into the type theory. So we did, but it went at first to a ho-hum. Nobody cared, like, oh, so what? You just made the theory more complicated. But it turns out, I think, to be a fundamental idea, and we use it all the time. Okay, so that gives you the flavor of some of these other types and what we can do with them. And I could stop now. What do you think, Bob, for time? I didn't. Okay, so I'll go a bit more. So I mentioned that uniform validity. So now I'm going to get to insights into classical logic. So at least we'll get that started. And to do it, I'd like to assign everybody an exercise. So here's homework or exercise. You don't have a whole lot of time to do it because my last lecture is tomorrow. But give a proof of this constructively true proposition. That's not hard. That is not very hard. But then Brouwer liked this a lot. You know, he said, well, this is a nice truth, and he has a beautiful English language proof in 2 sentences, but I couldn't find it this morning in all my notes, and I'm going to see tonight if I can find it. So why don't you try to not only prove it, but give an English. So Brouwer did it in like 3 sentences. So let's say English, 3 sentences at most. 3 short sentences. Why is this true? And what got me on to the topic I want to talk about next is every once in a while my colleagues decide to ask me why I went nuts and do constructive logic. So Andrew Myers was talking to me and he said, tell me again why you don't believe P or not P. And instead of answering like I've done for a lot of years, I said to Andrew, why do you believe it? So he paused just for a minute and he said, because it can't possibly be false. That was his answer. I said, is that it? That's why you believe it? He said, yes. I said, well, it's really this. This is what you're believing. And he said, well, that's the same. It's the same thing. But it isn't quite the same. And it was Kolmogorov, who, when he was 20 years old, he's certainly one of the greatest mathematicians ever. So Kolmogorov 20-year-old young whippersnapper, and I put down the date because it's so stunning. If I can't find it immediately, I think 1924, something like that. He said, I'll check the date. I found it, but put a question mark there now. He wrote this paper, and he said, we shouldn't use P or not P as the discriminator between classical and constructive logic. We should use not P implies P. And he said, look, it's simpler. This construct is simpler to understand. And so I was reading again about Kolmogorov, and it occurred to me that another one of our nice types, again, a type that Dana liked way back in 1983. We used this type that Mark has already mentioned, which we call the set type. I don't know whether that's a good name for it, but the set type has the property that to put an element in here, you actually have to know that there's a proof of B of A. So you're going to also have a proof of B of A in order to put A in this type. But you don't have to keep the proof with the type. Well, you don't. You squash it, is what we say, or you throw away that proof. And we did this for multiple reasons. One of them was it was looking to me like it was related to classical logic, but I didn't quite see how. But the reason we were discussing with the Koch guys when we used to meet regularly in Sweden, we said, look guys, this thing is the way to save extracts. When you're proving something like, say you want to define the natural numbers n as those elements of z such that z is greater than or equal to 0, that's a decidable property that you could check if you need to. So you don't have to, when you've proved this, you don't have to keep that proof around. If you need it, you could recover it. But this is going to save space in the extracts, like we were talking about. The extracts couldn't get large. Well, this was a way to make them smaller by saving whatever was put in here. Okay, so after talking to Andrew, I went back, and as I said, I was reading Kolmogorov, just one of his philosophical papers, which was quite interesting. And I said, well, what if we, instead of putting P here, what if we said we'll use the type unit with P sitting in there? And the type unit has just one thing in it, right? So unit is the type with, say, star in it. So what we would be saying if we added a rule like this, I was calling it classical introduction, we're saying, okay, I want to know about this type. Is there anything in it? And what do I know? I know that it cannot be empty. This thing can't be false. The type can't be empty, and there's only one guy in it, star. So you think, well, that's real close to almost constructive, right? You say, all right, look, we'll take this as our classical introduction axiom, and when we want to do classical math, this is what we'll use. And that's better than the Kolmogorov translation, where he went in and syntactically edited everything and put double negations in front of all the atomic formulas and double negations everywhere. And this one, and then he was able to prove for propositional logic that the two logics were equivalent. The embedding of classical logic was equivalent to classical logic, and Gödel extended this idea to first order logic. But with this, you could extend the idea to all of type theory. You just say, okay, if you want to do classical type theory, you just do this. You allow yourself this one axiom, and it's not going to hurt anything. So we've got that in Nuperl now, and we can prove a lot of interesting formulas that are squashed. Sometimes you have to squash a lot of stuff. Your thing might look like this, if you, in some cases. But when we want to do classical reasoning now, we don't do those embeddings. We just use this rule and have fun with the classical logic. So I'll say more about that tomorrow. But please do the exercise so we can compare the realizers. Okay? So I almost got all the way through. We'll finish up that stuff tomorrow.